Okay, we're on here is about, well, the title I guess I would have is Reynolds Transport Theorem. And it's going to be in one dimension. Well, a separate one of these that'll do the general case. Which is the same as this, but it's just geometrically much more intricate. And so this will be kind of the conceptual one, and then that'll be the one that gives you the powerful general equation. But it's much more involved in terms of its derivation. And as the last one of these little lectures said, this is something that allows us to convert between the Lagrangian notion of a chunk of fluid. And so this is a piece of fluid matter, and just like any piece of matter, the laws of physics apply to it, and its mass is conserved. Its change in momentum is equal to the sum of the forces on it. Its change in energy is equal to the heat and the work that go into it. And it allows us to convert between that, where it's easy to say those laws, and then allows us to apply them in an Eulerian frame, where it's a control volume. And so just let me give you a little example to make this a little bit more concrete. Consider a jet engine. So let's just say it looks something like that. And if we were to analyze the flow through this from a Lagrangian perspective, we would start off with a chunk of air that's going to go in. Maybe this might be at time t1. And this thing's moving to the right in the frame of the fixed engine. Maybe at some other time this chunk of fluid is somehow contained within the engine and very complicated inside. So this, of course, just means schematically where it is, and this might be time t2. And then later, this thing is ejected, is actually made hotter. It's had some heat added to it. It's got a little different chemical makeup too. In reality, it's moving a lot faster. It's had some forces added to it, and it's at time t3, and it's again moving out that way. So that's Lagrangian. Now that's kind of hard. You could talk about the thrust to the plane due to this chunk of fluid, but what you really want is just kind of the thrust of the plane as this thing's going along. And so this is the Eulerian perspective here, where you focus on the region of interest, and that would be the engine, and we're going to draw what's known as a control volume. Around it. So this is our region of interest is what the control volume is. And there's flow in, there's flow out, this chunk of fluid from the Lagrangian perspective, there's no flow in or out of that. That is the flow. It is the moving fluid. Here we've got this region of interest, and there's flow in and flow out, and this is the Eulerian perspective. And the Reynolds transport theorem, as I said many times now, allows us to convert between these. In many textbooks, this is referred to as the fluid system. It's not called a chunk of fluid. I like that better because I find it somewhat descriptive. This is the fluid system. And there it is at an early time, T2, T3. And that's what we can write down physical laws for. Okay, so that's sort of background for this. Let's define a couple other things. As we did with the material derivative, it's nice to write this kind of in general, so we can apply whatever law we want: mass, momentum, energy, the big three. And so I'm going to define a couple things. I'm going to define capital B. That's an extensive fluid property. These are properties that depend on the extent of what you're considering: mass, momentum, energy. And little b is the corresponding intensive fluid property. And it's going to be on a per unit mass basis usually. So, for example, if big B is equal to mass, little b is just equal to 1. Mass per unit mass is 1. If big B is equal to momentum, little b is equal to momentum per mass. Momentum is a mass times a velocity. Momentum per mass is then a velocity. And so on. And so we're going to come up with these formulas that involve big B's and mostly little b's. And we'll be able to say, well, you know what, if this is conservation of mass, well, little b becomes 1. If it's conservation of momentum, little b becomes v. And with this big B, how are these related in detail? Well, the big B is equal to some integral over volume of little b times rho times dv. So you've got some region of space. You might consider it broken up into little delta v's, each of which has a rho attached to it, a density. And so little b is a big B per unit mass. Rho is a mass per volume. Mass per volume. dV is a volume. And so it's the proper adding up of all of the little b stuff here. This has some little b associated with it over some volume. So there's some total volume here. There's some little delta v. We integrate over the volume. We come up with the big B. And there are two specific types of volumes we're going to define. The first being like this one, the fluid system. The second being like this one, this control volume, the region of space. And they both just have this formula, but let's write them down carefully here. And so this one's called the fluid system. And big B of this system would be integration over the system, volume of rho b dv. So this is attached to material. Particular pieces of matter that are in fluid form. And the other is the control volume. B control volume is equal to integration over the control volume. Same thing. And so this is a region of interest. Our physical laws, they say something about the system. This is the Lagrangian perspective. This is the Eulerian perspective. So if it's conservation of mass, we know that dB system dt is equal to 0. There's no change in mass of a mass. Momentum, dB system dt is equal to the sum of the forces. Energy, dB system dt is equal to the sum of the q dot in plus the w dot in, the heat and work flow into the system. So those are our laws we could apply. And we're going to do this first in 1D, and then we'll do it in the general case, as I said. So let's consider the flow in a duct of some sort. So just something, changing area. And let's just say for some reason we want to analyze flow in some section like this. And that's going to be the control volume. And we can't just come for that control volume and write down laws like these, because it's really hard to say that mass in that control volume can change. It's not equal to 0. We don't have a direct way to apply conservation of mass like we have here. Conservation of a mass tells us that its time rate of change of the mass is 0. Same thing for the momentum and energy. And so we need to relate what's going on with this control volume to something that involves a fluid system, or this chunk of fluid. And what we're going to do is say that, you know what, this is equal to the system at time equal. So we're going to take, though, that there's flow through this. And we're going to say that there's some velocity v1 here. We're going to call kind of this the one location, this the two location. We're going to say that there's some other velocity v2 over here. And then look at what happens to the system at a later time. Over here, it should move in. And this is the 1D version of it as was introduced. And so what we're going to say is that it moves in uniformly at all locations here. It's flowed in the same way. That's the 1D. And at all locations here, it's flowed out the same way. That's the 1D aspect of this. And let's just say, let's put in this little bit of notation here, that this amount that it's flowed in is some delta L2 here, and this is delta L1 on this side. Okay, so what I want to do is relate, oh, and of course this is then the system at some later time, but let's just say it's a little bit later, delta t. Okay, so how is the control volume related to the system now that we've defined this? The system, this mass of fluids within the control volume, and then a little while later it's flowed to the right. Well, we can say two things here. We can say that at time t equal to 0, B system of t is equal to B control volume t. T is equal to 0, or it can just be, it can be any t, and this is delta t later, really. Delta t later, we have B system at t plus delta t. And then let's see what happens here. That's equal to the stuff in the control volume still. So that overlaps. But it's at this later time. And then two things happen. The system has, in addition to the stuff that's still in the control volume, it's got this region 1 here. Let's call it I. Plus BI. Or this one's actually 2. It's supposed to be kind of like II2. B2. And so the system has what's in the control volume still, plus that, but then it also has, it doesn't have this stuff over here. So it's got minus B1. And so this is region 1. So these regions where the system's moved off of the control volume, well, it has that there and this region here. And so this is true at this later time. And then what we can do is subtract these and divide by delta t. And so we end up with B system at t plus delta t minus B system at t all over delta t is equal to B control volume t plus delta t minus B control volume t delta t plus B2 over delta t minus B1. That's supposed to be 2 over delta t. Okay, I want to look at these in a little bit more detail. What is this B1? Well, it is a little b in region 1 times the density times a volume of region 1. And if you look up here geometrically, there should be a relationship between the volume of that region 1. We can call there's an area of region 1. So that volume would be equal to B1 rho 1 delta L1 times A1. So if this is well approximated, if this has gone just a little way, the volume of this region would be the area times its height, approximately. We neglect the little slope part in this case. And there's just an additional thing we can say. If it's a short amount of time, we could say it's B1 rho 1 B1 delta T A1, because this will move in times delta T from here to here. The distance it'll move would be the velocity times delta T. And of course B2 rho 2 V2 delta T A2. Okay. Let me rip this off. And show how this is going to simplify. This is just a derivative. Small change in delta t and the arguments up here over delta t. So that'll be dB system dt. That's good. This is the thing we can write down laws for. This will be 0 or some of the forces or the heats and works. This control volume one is also a time derivative. That'll be now these other ones, these that come from the little regions in and out here, well, we're looking for like B2 over delta t or B1 over delta t. These both have delta t's, and so those just divide out. And what we end up with here is plus B2 rho 2 V2, not volume V2, V2 A2 minus B1 rho 1, not volume, B1 A1. And this is the 1D version. These all have meaning. Let me just label those here. This is the law. It's the creation or destruction of B stuff. It's 0 for mass. This is storage. Forget about flows in and out, get rid of these terms. And you can see that if the law tells you you have more mass, then there's more mass stored in the control volume. This is a flux out. So forget about this last term. If you create B stuff by whatever physical law you have, some of the forces, and it's not stored, so let's say that's 0, well, then it better be a flux out. And this is the opposite. It's a flux in. So let me just show you one particular example of this, bringing us back to something we already know. Let's look at mass. Conservation of mass. dB system dt is equal to 0. You don't create or destroy mass of a mass. So and let me just say one other thing. B is equal to 1. Mass per unit mass. Little b is equal to 1. So we have 0 is equal to partial B control volume plus rho 2 V2 A2 minus rho 1 V1 A1. That's just going up to this expression. Little b's become 1. Writing this one. If it's steady, no storage, you're not accumulating any mass in this control volume, dB control volume dt is equal to 0. And we have then that rho 2 V2 A2 is equal to rho 1 V1 A1, which is something we introduced previously as this m dot 1 is equal to m dot 2, and kind of used in conjunction with solving Bernoulli's equation, or analyzing different systems in conjunction with Bernoulli equation. If density is constant, you have it in the form we've used the most. B1A1 is equal to V2A2. So this is consistent with that idea that we introduced, but it comes from this more general framework. It's a very, very special case of this more general result. It's a special case even of just this 1D result, and I think we'll come back to this when we analyze the full 3D equation.